Okay, so good evening everyone from India. Welcome to free webinar on PVT modeling and advanced fluid characterization, a focus session designed to unravel the science behind behavior and its fluid behavior and its impact on reservoir performance. I'm Swapnil from Edvantage team, and it's my pleasure to have you all with us today. It is now my privilege to introduce our esteemed speaker for the session, Mr. Vinod Kumar Madem. Mr. Vinod is seasoned reservoir engineer with a strong background in reservoir simulation, modeling, and fluid characterization. His journey in oil and gas sector includes hands-on role at reputed companies such as Oilmax Energy Private Limited, Sun Petrochemicals, and Rare Energy Consulting, where he worked on diverse fields and cutting-edge reservoir technologies. From supervising well tests to developing EOS model, he has led initiatives that contribute directly to performance optimization and economic evaluation. Today, he will walk us through PVT data acquisition and analysis, EOS modeling and tuning, advanced fluid characterization techniques, reservoir fluid phase behavior. Now, without further ado, I now invite Mr. Vinod Kumar Madan to take us forward with the session. Thank you very much and enjoy the webinar. Over to you, Vinod sir.
Yeah, thank you, team. I'll start.
Yes, yes, sure.
Yes. Okay, welcome to this free webinar on PVT analysis and fluid modeling. So, anyone in the audience who can just expand what is PVT? I just want to see. Anyone? PV and T. Okay, so P is pressure, V is volume, and T is temperature. So with this analysis, we try to understand the relationship between pressure, volume, and temperature of any fluid. So in the oil and gas industry, it is for hydrocarbon fluids. So with analyzing that relationship, we build a fluid model that works at all pressures and temperatures and volumes of the field life of production, right? So first things first, why should we understand phase behavior? So whenever we discover a field and we think of producing from that field, we need to understand what is the initial reservoir pressure, PI, and reservoir temperature, T reservoir. After knowing this and doing some studies from seismic to simulation, we will understand what is the volume in the reservoir, volume of hydrocarbon. So we need to understand how these three variables, pressure, volume, and temperature, vary with production and as well as time. So whenever we produce, maybe some after some point of time, oil and gas are subjected to pressure, temperature, and compositional changes. So to track these three parameters, we need to understand the phase behavior of that particular hydrocarbon fluid. These changes affect the volumetric and transport properties of fluids. So the main basic thing of this course is that we will like walk through all the areas where this pivot analysis is used in the industry. So this 5-day course will focus on every aspect of this particular topic in all oil and gas industry operations, not just reservoir engineering. In primary depletion, where your pressure drop is the primary driving force for oil and gas to produce, and of course in secondary recovery technique, which is water flooding, fluid properties are represented through black oil definitions. So black oil definitions is when your oil is a single component and its composition is defined. Similarly, gas and water, but there is no mass transfer happening between two different fluids or phases. But in compositional, we will also track the mass transfer and that phase behavior. In enhanced oil recovery, phase behavior of reservoir fluids and injected fluids. The primary aspect of enhanced oil recovery is that we try to go for chemical flooding or thermal stimulation, thermal flooding, microbial enhanced oil recovery. So these all will, like, we need to inject something into the reservoir. So in an enhanced oil recovery, we need to understand the phase behavior of reservoir fluids as well as injected fluids, whatever you're injecting. And this behavior is used to classify the recovery method, which is either thermal, miscible, or chemical in case of enhanced oil recovery, and to design the recovery process. So why do we need to classify fluids? Whenever we do fluid sampling, which is generally done by uh, two techniques in the industry. One is RFT and MDT. So RFT is repeat formation tester and MDT is modular dynamic tester. So these two have PVT cells or chambers which go into the well whenever the well is not cased. Okay. So we need to have the reservoir or phase zone open. It should not be cased. And then we go and collect the representative fluid samples. So to determine the fluid sampling, we need to classify reservoir fluids and determine types and size of facilities and surface equipment. Depending on the your hydrocarbon GOR, which is gas oil ratio, we need to also keep planning or plan initially what should be the separator size, and the storage tank volume, depending on the volume of oil we are targeting to get or produce from that well or the field. Dictate depletion strategy to estimate oil and gas reserves, determine the applicable enhanced oil recovery method, and also material balance calculations. As far as classification is considered, primarily oil fingerprint is quite important, where we try to understand what is the mole percent of each of the carbon number from C1 to C90. So whenever we send the PVT sample or the hydrocarbon fluid sample to any lab, which tests and gives us several results, it will give us oil fingerprint. So we will also be showing you how the testing is done, testing will be done, and how we'll get the report in the actual course. So from C1 to C90, we'll have the mole percentages of each of these components. And also we need to look at SAR analysis, which is saturates, asphaltenes, resins, aromatics. So these four components of any hydrocarbon fluid is quite important because we need to plan or design the surface facilities, including storage tanks, separators, as well as pipelines for metering. So depending on these four components, we will plan if my oil or gas is going to form hydrate at surface or in the wellbore, or is it going to is it going to give out wax whenever temperature goes down a certain temperature window of wax appearance. So this will give you that idea. And also we can primarily get API gravity and specific gravity. So API gravity is nothing but 141.5 by specific gravity of that fluid minus 131.5. So generally, since water has specific gravity of 1, your API gravity of water is 10. So if the API gravity of our hydrocarbon fluid is less than 10, it is heavier than water. And if it is more than 10, it is lighter than water. And also to define the pore and cloud points. So what is my pore point of the fluid? So at what minimum temperature will the fluid be able to flow in flowing condition? And if that hits a temperature, it won't flow. It will form clouds. And also we can get sulfur and asphalt content depending on the oil fingerprint. Okay. So we'll have mole percentages for each of these components, including carbon dioxide, nitrogen. So where does PVT data be useful? So the primary part where it is useful is simulation. So in simulation, when we prepare a fluid model, either black oil or compositional. So for compositional, it is quite difficult and complex to prepare a fluid model where we need to honor and continuously regress the lab estimates of several properties or several curves. So we'll discuss that in detail in the course. And also in EVA process, PVT properties to estimate them, hydrate formation, which I've discussed in the last slide, asphalt and deposition or condensate banking, emulsion formation whenever it flows, scale formation whenever it flows, designing facilities, understanding the flow properties, and of course, reserve estimation. So when we estimate reserve, what we do is we calculate the hydrocarbon in place, HCIP, which is area times thickness of the reservoir times porosity times 1 minus SWI of the water saturation. This is water saturation. So 1 minus that gives me oil saturation. Sometimes we also divide this with BOI. So BOI is nothing but oil formation volume factor, which is volume of oil at reservoir condition by volume of oil at stock tank condition. So this oil FEF, we will be getting it only from PVT analysis. So this has this kind of behavior. So whenever bubble point pressure is known to us, and when the oil tracks that, so below PB the BO decreases, and of course above PB the BO decreases. Okay. So whenever I try to understand the expansion of oil, I'll take BO at any pressure and BOI at highest pressure where reservoir is found. So expansion of oil term is BO minus BOI. Expansion of oil is due to expansion of the dissolved gas in that oil. So whenever I want to convert my hydrocarbon in place from reservoir units to field units, I will divide this entire volume of reservoir or the volume of hydrocarbon in the reservoir to stock tank conditions by using BO. So because oil FEF has a unit of barrel in the reservoir by barrel at surface. So if I divide this entire equation with BOI, I get barrels of oil at surface. Okay. That is how we can also plan for surface facilities for storage. So we should and first and primarily understand the fluid phase envelope. So this is also an output of PVT analysis that is done in lab, and after we develop fluid model, the software will give us this kind of fluid phase envelope. So if you can see, there are 3 points, 1, 2, and 3. So this fluid phase envelope is a plot of pressure and temperature. So you have a phase envelope like this. In this phase envelope, you have bubble point curve on the top and dew point curve on the bottom. So dew point curve is that curve which divides the two-phase region with the single-phase gas region. You can see gas phase here. But bubble point curve is that curve which divides oil region or liquid phase region with two-phase region. So if you go from top to bottom in this direction, you can see your liquid decreases and gas increases. So these quality lines are those lines which give us the composition or component percentage of gas and liquid. So this line corresponds to 50% of each phase, liquid and gas. So if you can see the declining pathway of pressure at a constant temperature, I'm sorry, yeah, 1, 2, and 3. So 1 is the point where it is single phase liquid. But when it hits 2, due to pressure decline of production, it will start giving out gas. And at 3, it will give more gas. And this continues further like this. So this kind of isothermal pressure drop will give us or let us know what is the pressure declining trend and also what is the composition of each phase with at that certain pressure. This is quite critical in fluid modeling. So whenever we talk about single component system or pure fluids, same plot of pressure and temperature, but it is single component. So we have solid phase, liquid phase, and vapor phase or gas phase. So solid phase and liquid phase is divided by fusion curve, liquid and gas by vapor pressure curve or vaporization curve, and solid and gas by sublimation curve. So the point joining these three is triple point. So you can see triple point is that point of juncture between these three lines of divisions or curves. But in two component system where you have liquid and gas alone, so it will be critical point and not vapor or triple point, right? Critical point above this will be supercritical region, SC. So whenever your temperature is more than critical temperature and pressure is more than critical pressure, this region will be supercritical region. It should technically be a liquid only, but yeah, we call it supercritical. Okay. So critical pressure is a maximum pressure above which only liquid is found. And sorry, critical pressure, yeah. And yeah, critical temperature is the temperature above which only gas is found. Okay, quite simple. So in multi-component system, if we need to talk about a certain example from reservoir, which is retrograde gas condensate reservoir. Okay. So you can see in multi-component system, depending on the carbon numbers, your fluid phase envelopes always shift. So when your pressure drop dictates your amount of gas and liquid in the reservoir, your uh, phase envelope will shift towards top or bottom, depending on the composition of each carbon number based on the hydrocarbon footprint or carbon number footprint, which was in the very beginning slide. Your oil fingerprint, it matters the most at the certain pressure and temperature. So retrograde region, I'll discuss this in the later slide. I have a beautiful slide for this. So reservoir type based on phase behavior. So whenever the initial reservoir pressure is above the critical point in temperature sense, it is dry gas reservoir. But if it is close to critical or dew point line, it is wet gas reservoir. Retrograde gas condensate is that reservoir where your initial reservoir condition is in between critical point and the dew point curve. Black oil reservoir is that reservoir which has initial reservoir condition between bubble point curve and the critical point. Volatile reservoir is that reservoir which has the initial reservoir condition close to critical point, meaning critical pressure and temperature. Also, reservoir types based on composition and production. So, gas condensate reservoirs have GORs, which is gas oil ratio. This oil is actually condensate between 70,000 to 1 lakh SCF per STB. SCF is standard cubic feet per STB stock tank barrel. And gas condensate reservoirs have density greater than 60 degrees API. They are light in color, and the composition of C7 plus is close to 12.5% because they have rich components or heavier components. Similarly, volatile reservoirs or volatile oil reservoirs have GOR between 1000 to 8000 SCF per STB. Density is in between 45 to 60 degrees API. Oil FEF are greater than 2, which is BO. So BO is volume of oil at reservoir condition by volume of oil at stock tank condition. So whenever BO is more than 1, it means volume of oil at reservoir condition is more than volume of oil at stock tank condition, right? This is quite common in volatile reservoirs because whenever volume reaches surface, your like gas escapes out of oil. So this volume shrinks or decreases. So they are called as high shrinkage oils. So this volume shrinks more as compared to black oil reservoirs, which are low shrinkage oils. Okay. So black oil also have GOR less than 1000 SCF per STB, density less than 40 degrees API, and temperature of reservoir is less than 250 degrees Fahrenheit. And they're dark green to black in color. So depending on each of the fluid compositions, you can see the component mole percentages. So black oil has least C1, but wet gas has highest C1. Similarly, gas condensate has the C7 plus in larger number. Molecular weight is 112 and also 3.8 is quite high. But black oil also has C7 plus of more in quantity or mole percentage. So this oil FEF relates reservoir volume of oil to surface volume. The reservoir volume includes dissolved gas, while surface volume is essentially dead oil, just no dissolved gas. Similarly, solution gas oil ratio, RS, is a measure of the gas dissolved in the oil at any given condition. So it has the units of SCF per STP or thousands standard cubic feet per stock tank barrel, MSCF per STP. Similarly, viscosity is a primary output of PVT analysis, which is a measure of resistance to flow. As the pressure is decreased below bubble point pressure, the oil viscosity increases due to release of solution gas. So there is nothing volatile in that oil. So oil is becoming heavier and viscous. Above bubble point, the liquid molecules are forced more close together and oil viscosity again increases as the pressure increases. So if you can see the plot of viscosity, it will be increasing above the bubble point and also below the bubble point. This is the viscosity plot. This PB. Pressure is this, viscosity of oil is this, right? At bubble point, viscosity of oil is minimum. The oil viscosity is strongly dependent on temperature, dropping exponentially with increasing temperature. So black oil properties, you can see the the plots of each property. So RS, it is constant above bubble point pressure, but it decreases below bubble point pressure. Similarly, oil FPF, it decreases above bubble point pressure and also decreases below bubble point pressure. Similarly, viscosity, it increases above bubble point pressure and also increases below bubble point pressure. BG, which is the gas formation volume factor, it will decrease as pressure increases. So BG is nothing but volume of gas at reservoir condition by volume of gas at stock tank condition. Of course, when pressure decreases, your volume of gas at reservoir condition is highest, right? It will keep on increasing. The volume of gas expands. Gas is highly compressible fluid. And also viscosity of gas increases as pressure increases. So this is how we define the oil and gas PVT properties. So BG comes from this separator gas to gas in reservoir, right? That is how we define. So oil, so I'll discuss more with fluid studies. So we do flash liberation test as a part of laboratory examination, differential liberation test, constant composition expansion test, constant mass expansion test, constant volume depletion test, multi-stage flash separator tests, viscosity measurements, and composition measurements. So we do sampling bottom hole, like we take it in the bottom hole, so it will be preserved at reservoir temperature and pressure condition at reservoir conditions. Selective sampling zones is also possible with several sophisticated tools, and sampling early in the life of reservoir with minimum disturbance is quite important. And of course, we need to have a lower overall cost. So we have bottom hole samples or subsurface samples. Similarly, we have separator samples where we do recombination after taken to the lab. Okay, if we don't have provision to take bottom hole samples, we take surface samples and we recombine them to get or bring them back to reservoir conditions. Soil properties are bubble point pressure, oil formation volume factor, solution gas oil ratio, total formation volume factor, CO and mu, which is oil compressibility and oil viscosity. Similarly, gas properties include gas compressibility factor, gas formation volume factor, and gas viscosity, and of course, composition of oil and gas. So first test, flash liberation. So what we do is we power up the cell with helium, which doesn't react with oil, and then we decline the pressure slowly, hoping that after the pressure goes below bubble point pressure, a gas starts coming out of oil. So we don't remove this gas. We keep the gas in equilibrium with oil, and we try to measure what is the oil volume in the PVT cell. This is the PVT cell. So results would be number of phases in the reservoir, molar composition of each composition of each phase, and of course compressibility factor of gas. Next is differential liberation test, where we will remove the gas that comes out of oil. This test is designed to approximate the conditions in the reservoir where gas is released from solution as the pressure falls and the released gas moves away from the oil as a result of gravity segregation. So from this test, we can measure many properties, unlike flash liberation. Third test is constant mass expansion, especially for gas condensate. So we try to decrease the pressure with mercury, and then we try to see how much condensate is dropping out of gas. So this condensate drops out as a result of heavier components being shrinked out of gas. Okay. So we can also try to get the dew point of this reservoir. The way we get bubble point in black oil through flash and differential liberation tests, we get dew point of gas from CME and CVD. Okay. So let's understand retrograde gas condensates, which I was talking before. So generally the initial reservoir condition is in between critical point and the dew point. So whenever the pressure drops below this initial reservoir condition and enters two-phase envelope, initially what happens when pressure drops, generally gas will try to expand, but here gas will try to shrink and liquid starts dropping out of gas. You can see the tie line, the quality line. This is the line where your liquid is again coming out of gas. Okay. When the pressure declines after production and reaches the dew point pressure, the first drop of liquid is observed as it falls in constant mass expansion test. The oil drops out of gas, which is the condensate. Further reduction in reservoir pressure increases the liquid volume and reduces gas volume as depicted in the figure in the two-phase region. Liquid volume reaches to maximum at point number 2. This is the point where it reaches maximum, and again liquid starts dropping out, or liquid starts revaporizing out to gas. And this further reduction in pressure causes reduction in liquid volume and increase in gas volume again. So liquid starts vaporization and liquid volume becomes almost zero at low pressure. This phenomenon is called as retrograde gas condensation. Okay. Similarly, we have another fluid which is called as near critical retrograde gas condensate. So this point is close to critical point in that reservoir. Okay. So that test which approximates this phenomenon is constant volume depletion. So similar to differential liberation, we try to take out gas at each step of pressure decline. Okay. Once the oil drops out of gas. So gas will be removed, and we will see how much oil we can get out of this gas, which is the retrograde gas condensate. So we can get the dew point pressure, two-phase Z factor, recovery of oil in place. So this can give us P by Z versus GP plot. So this plot is quite important. So whenever I plot P by Z versus GP gas produced from this PVT cell, I'll get a straight line. Okay. So this straight line is telling me that it is a pure volumetric depletion drive system in the reservoir. That means pressure drop is the only thing. But if it is going above this, okay, it is water drive. So there is water supporting this uh, pressure depletion. It is flowing it down. So if I extrapolate this, I can get my gas in place, GIP. So we'll get pressure as well as the compressibility factor of gas from this experiment. And also we can get how much gas we can produce out of this PVT cell. Separate tests include where we try to bring down pressures in different stages, and we will try to remove gas and oil at each stage of pressure decline. So we can get how much gas we can get at standard condition, and also how much stock tank oil we can get at standard condition. That is the primary thing of separator test. This is the money that I get out of production, right, at separator. General characteristics: black oil has GOR less than 2000 ST per STB, oil gravity less than 40, and FEF less than 2. So black oil is generally low shrinkage oil, but volatile oil is high shrinkage, right? HS. And GOR, it is in between this range, 2000 to 3000 ST per STB. It is orange to brown color. Oil gravity is more than 40. Dry gas, it has high GOR. It is mostly methane, C1, and it has high GOR, more than 1 lakh SCF per barrel. Wet gas, it has less GOR as compared to dry gas, and the liquid API of condensate is more than 50-degree API. And retrograde gas condensate, GOR is reached up to 6000 ST per STB, and the quality is, it has more than 50-degree API, and it is whitish in color, the gas condensate, the condensate. So now, once we understand all this from lab, we will try to build an EOS model, which is the equation of state, which is again called as fluid model. So EOS model is just to give us the phase envelope, right? And also different curves that we use. So generally, we have several EOSs for both single component systems and multi-component systems. So EOS are generally mathematical relations between pressure, temperature, and volume. But in multi-component, we'll also include molar composition of each component with a set of mixing rules. That is what I'm telling. We should also look at mass transfer between the phases. So assumptions for ideal gas are generally molecules have zero volume, and we don't consider interaction between the molecules, right, in ideal gas. So SRK equation of state is one famous equation of state that we use, and also Peng-Robinson equation of state. We also have Peng-Robinson modified and other equation of states, which we'll discuss briefly in the course. So our main idea is to just get the fluid phase envelope, and also understand relationship between pressure, volume, and temperature. Okay. So where is PVT used? So we use PVT in classical reservoir engineering studies like material balance, PTA, and decline curve. So PTA is close to well testing. What data we get from field, we interpret that in software using PTA, and also decline curve analysis. Because your BO, which is the oil formation factor, varies with pressure drop, right? So quite important in DCA. And also reservoir simulation, especially in compositional simulation, where we build a fluid model primarily for simulation study, and we understand how it is working with production. And also oil and gas metering. So to design pipelines, storage tanks, and processing facilities, we need a detailed PVT report. That is the main input for designing team, okay, the operations team. And software that we use for PVT modeling is, one is PVT Sim, the famous software from Calcip, and PVTP from IPM, and also WinPro from CNG. So we will touch two among these softwares. One is PVT Sim and also WinPro in the course. So I'll see with time if I can touch only one or two. But yeah, we will do at least WinPro in the course. I'll give you a hands-on with WinPro, right, to build a fluid model. So what is the course? I'm sorry. What is the course structure? Okay. So module 1 is introduction to PVT and fluid properties. Module 2, we will try to do e-voice modeling, primarily to get the report from lab and analyze that and build an e-voice model in a software. And we will see how it is applied in reservoir engineering, especially from material balance and decline curve analysis, and of course simulation. And we will also look at PVT modeling applications in production practices. So we need to understand how the phase behavior is in the reservoir, not just in the reservoir, but also in the wellbore till surface. When it reaches surface, when is the gas separation happening in the wellbore, right? And also module 5, we will look at practical fluid modeling through software and of course case studies. So one of the primary importance of this course is we will build a fluid model for CO2 sequestration with reference to that, right? We will build a model especially for this. So I'll just give you hands on how we can build a fluid model for CO2 injection for sequestration, right? So CC is the booming word right now, carbon capture and sequestration. So I just want to give you some fundamentals of how we build a fluid model and how we can actually run a simulation run for sequestering CO2 in subsurface formation, right? We will do that through WinPro, CMG WinPro. Yeah, I think I'm done. Any questions? You can just ask me. Or anything you want to add in this course structure, you can just let us know now. Okay. So thank you. If you have any questions, you can just also put in the chat box. Yeah, I think I got some questions. Okay. What is SARA analysis? So yeah, let me just write it here. So SARA, SARA. So S is saturates, asphaltenes, resins, aromatics. So saturates are straight chain carbons, asphaltenes, branched carbons, resins, branched carbons with inorganic components like nitrogen, oxygen, and aromatics are benzene ring components, right? So PVT lab will try to give us the composition of each of these components: saturates, asphaltenes, resins, and aromatics. This will give us an idea that how do I look at flow assurance issues in my whenever this crude that I produce flows at all systems, right? Yeah. Yeah, we will provide slides and recordings. Yeah, sure. Any other query? Anyone? Yeah, I'll try to reduce my speed in the course. I'm sorry. Yeah. When we use Peng Robinson correlation, SRP correlation. Yeah, whenever we try to regress the lab data to the PVT model, we will try to apply some regression parameters. That is where we see which equation of state model is applicable to that kind of fluid that we are analyzing. So we cannot just tell which to use when, but yeah, we will understand when we start building the model and see which equation of state model is applicable to that fluid that we're analyzing. Okay. So it's a part of regression process. We will see in that which model is quite applicable to that. But as industry progresses, Pengue-Robinson equation of state is quite like common to be used than SRK equation of state. I myself used PR equation of state a lot of times in my reservoir engineering studies for fields. Yeah. Okay. Yeah. I think I'm done. If anything else, let's just get back to our team and we will be happy to help you. Yeah.
Okay, fine then. Can we wind up?
Yeah, sure, team. Sure.
Okay. Thank you everyone for joining. And we will share the recordings with you. Thank you.